The following is a presentation by Rodney Herring from the University of Victoria for the International Conference on Material Science and Nanotechnology being held in Prague, Czech Republic, June 25th and 26th. The title of my presentation is The Production of the Effective Germicide Photocatalyst. And it's going to be focused on stearicline crystals, which is the name given to iron-doped titanium dioxide. And these crystals you will see are very powerful, and we sometimes say they are a solution looking for problems. So the background is that the stearicline crystals are based on titanium dioxide, which is FDA and Health Canada approved for unlimited consumption in our food. We've been eating these for about 80 or 90 years with no notable side effects. Uh, the thing about the crystals I'm talking about is that they can be made large, uh, greater than 100 nanometers, so greater than nanotechnology, and this addresses the European concern. Titanium dioxide is used as a food thickener, cosmetic-based, toothpaste, quite a bit in our society. Titanium dioxide also makes up the paint in our houses. And I'm going to be showing that these crystals, iron-doped titanium dioxide, called stearicline crystals, have been independently tested for human safety at government-approved laboratories. For any kind of applications for use, all they require is labeling. The, the thing about pure titanium dioxide is that it requires ultraviolet light to activate and generate hydroxyl radicals. And ultraviolet light is expensive, and its exposure to humans is carcinogenic. But also, any kind of charges generated by the absorption of ultraviolet light has a very high recombination titanium dioxide, making its efficiency as a catalyst very low. Also, ultraviolet light doesn't pass through glass except for expensive quartz. And ultraviolet light doesn't easily pass through water and absorbed within a few millimeters, so deep penetration is not possible. So the crystals I'm going to talk about, iron-doped titanium dioxide, can be activated to produce massive amounts of hydroxyl radicals using both light and electricity. Perhaps these crystals are the most efficient producer of hydroxyl radicals. And when we find that we produce them using electricity, using a hydroxyl radical reactor, they're very efficient, even at low powers. So how did iron-doped titanium dioxide, the science behind these crystals has been known from the 1970s, and one can see publications going back many decades. And the problem with them is that they weren't working very well, even though they should have been working very well. And what was found when we made up these crystals is that there was a surface contamination on the crystals, and the contamination was not enabling the atomic planes to extend to the surface. We can see here in this TEM image that this modelly structure here is contamination, and sometimes the contamination is just 1, 2, or 3 atoms thick. So when we looked at what this contamination was, we used X-ray photospectroscopy, and we determined that it was the iron oxide. When we removed it off, we washed the crystals, we found that the activation of these iron-doped titanium dioxide went from about 4 to 10% right to 100%. And you can see here when we cleaned it off that now the surfaces of these crystals are very clean, absent of that contamination layer. Also, you can see we make these crystals using the sol gel process, which is the cheapest process. And the crystals are not even close to being uh, perfect. They have a lot of edges and corners. But we actually like a lot of edges and corners because that's where the charges are released from the crystal during their catalytic activity. If we look at the crystals that we're producing, we see that they have a range in size from less than 100 nanometers right up to greater than 50 microns. The small crystals actually outnumber the large crystals, but the large crystals make up the majority of the volume of the powder of the crystals. So what we can do is we can actually separate out the small crystals from the large crystals using a cyclone filter. And this addresses the European concern about these crystals being nanotechnology because we can make them greater than 100 nanometers. And the thing about these crystals is that they're very efficient in producing hydroxyl radicals. We see the hydroxyl radicals have very high oxidation potential, 2.8 volts, much greater than that of ozone or hydrogen peroxide or chlorine. And so really the focus is to produce as much as possible these hydroxyl radicals as they're the strongest oxidizer. The hydroxyl radicals indiscriminately degrade many things, organics, ammonia, pharmaceuticals, forever chemicals, some forever chemicals, metal organics, coliforms, bacteria and viruses, mold, and all these nasty things. And the nice thing is there's no biological response to hydroxyl radicals, so they can't change genetically to overcome them. If we look at the difference between these stearicrene crystals and regular titanium dioxide, we see that they are about 10 times more efficient in producing hydroxyl radicals. When we test them with E. coli, we find that if we put them onto surfaces and then shine a visible light onto the iron doped titanium dioxide, we see that they degrade E. coli over time. As well, here we see that this is actually quite early data, but it was very favorable in being able to degrade, eliminate cells over time. If we look at the crystals when mixed with E. coli and then image them or shine visible light on them to activate the crystals and then image them with the scanning electron microscope, we can see that when the crystals touch the E. coli, they eat holes into the cell membrane and cause the E. coli to lyse. If we look at these crystals with their how they keep surfaces clean, we can see that if we treat surfaces, this is in a restaurant, they're able to keep the surface germ-free over several weeks. After 3 weeks, we start to get little colonies coming out. But if we clean the surface, this goes back to being protected by the crystals. Whereas if the surface is not treated, they immediately start forming these colonies in the agar plates as seen here. This also shows the effectiveness against the crystals against surfaces where there's fungi present. And we can see here that no fungi were able to be present on the surface that was treated versus a surface that wasn't treated. You can see there's a very nasty fungi here. Also, there's some practical applications in sports clubs where they have bad mildew in the changing rooms and showers and things. If the crystals are applied to these surfaces, they can keep the surface mildew free for years. All they require is full spectrum lighting to activate, and you can see the big difference here between treated and non-treated surfaces where the mildew comes through the paint. So independent tests have shown that these crystals are effective against E. coli, staph, rotaviruses, and coliforms. So we have in Canada Keystone Labs in Edmonton, which tested these crystals, and we found that they were both effective up to 99.8% against E. coli and staph greater than 93%. This is really very early data, but it shows that the effectiveness of these crystals on surfaces. In addition, they were tested against the COVID rotavirus, and we find that they were very effective here in these tests at the Center of Chemical Biology at McMaster University, following the ISO 21702 guidelines, and 99% of the rotaviruses were eliminated. This is an independent test for a hospital in Thailand where they had the crystals were used to clean hospital wastewater, and their water started with 49,000 coliforms per 100 milliliter. When the crystals were used, after 1 minute, they were able to reduce the number of coliforms to less than one after 1 minute. So a nice 4 log reduction. Also, there's independent tests that show that there's no toxicity of these crystals to human cells. Again, it was carried out at the Center of Microbial Chemical Biology at McMaster University. And we find that when the crystals are mixed with human cells, that they are non-toxic. Anything that's around one here is non-toxic, so they were tested over a wide range of dilution. So you can imagine these crystals are very good for hospitals, which are the biggest transfer of disease. So they're always active. All they require is full spectrum lighting. And this is one of the targets for its applications. We can also put these crystals onto porous glass and composites. In these, you can see here, this is fiberglass cloth, and you can see the crystals on the cloth. They stick on really, really strongly. They don't come off, including a composite here, a metal ceramic composite. This enables us to produce reactors. Here's some example of the reactors, and we can make them pretty well any size. And so now with these reactors, we're activating the crystals using electricity. And these are very good at keeping water sources disinfected and So if we want to look at some of the effectiveness of this, I'm going to just quickly show here. Hopefully I'll be able to show this quickly. So here we see a beaker with water in it, and it's the reactor with one of the electrodes having the crystals on it. And we're going to add methyl orange. The methyl orange is a very strong dye requiring 2.5 electron-volts to degrade. And we can see that when it's added to the water, that the reactor degrades the methyl orange very, very rapidly. The other thing that's rather interesting is that we can put the reactor into water, let it run for a little while. And when we do that, we find that uh, the water remains uh, highly oxidative afterwards, after the reactor's taken out. And you can see that here. So we take the reactor out of the water. We're going to let it clear, let it sit for a while. And now if we add the dye, methyl orange, we can see it degrades immediately. So it shows that there's continued oxidation of the water, and this is just essentially tap water that we're using here. So this is shows the good effectiveness of the crystals as reactors. We can see that the degradation rate is extremely high. Uh, and just taking a minute to clean out large volumes of water. It's very difficult to measure hydroxyl radical production, but if we uh, put in some benzene into the solution, when hydroxyl radicals react with benzene, they produce phenol. Both of these are very easily measured using a UV spectrometer. And we find that it takes approximately these hydroxyl radical reactors producing about 4 electrons to generate one hydroxyl radical. And our championship data is that it only takes about 2 electrons to produce one hydroxyl radical. These are the supporting publications of this. It goes back to 2018. And so it's been well published. You can see that it's been well patented. The one up here in blue is the foundation patent. If you're interested in this technology, you can contact me to request more information. And it's all possible because I have a very powerful uh, electron microscope that's able to see about down to 1/10 the size of the atom, which showed me that there was this contamination of iron oxide on the titanium dioxide crystal. And so when we cleaned it off, it activated it very well. So conclusion, don't use abnormal cleaners, use stereo cleaning crystals for what they're worth. And that's the end. Thank you very much.